We have been introduced into how to start making sense of our data, not necessarily by analyzing this data, but instead by looking at the patterns or the shapes that our data are creating. And today we're going to continue working and building on those ideas. We're going to continue looking at the different patterns that our data are going to be making by using other forms of descriptive statistics. And this type of statistics, again, are exactly what the name implies. They're just simply used to describe what our data set is. So again, we're still not working with the data in a way to test any kind of predictions. That is something that's going to come later in the semester. Now, one of these things we have already talked about and kind of work with, which is the visual representations of our data. So specifically, we work with frequency distributions. And again, just by looking at the shapes of the distributions that this, for instance, bar graphs are making, we can already say a lot about the type of data that we have. Now, today we're going to focus on other two big things that they're easy to calculate to an extent. And they're simple forms of statistics, but they tell us a lot about the human behavior that we're trying to learn about. And those are going to be central tendency and variability. Central tendency measures describe what is a typical score in a distribution. So again, for the most part, this type of measures are going to give us a quick view of what is the most common outcome of the human behavior that we are interested in when we're looking at all the people that we have made observations from. Now we have three main measures of central tendency: the mean, the median, and the mode, all of which I'm pretty sure you're all familiar with. But we're still going to discuss very quickly, just to refresh our memories, on how those are calculated and what kind of information they provide for us. The mean is the average of the scores in a distribution. To be able to calculate the mean, all we simply have to do is to add all of the different scores or observations that we have in a data set and then divide them by the total number of scores or observations that we have in a database. And again, this is something that you're most likely extremely familiar in how to do. But again, just as some quick reminders, we do have here the formula notation. Now, again, this formula notation might be a little bit strange to you just because you're not used to seeing it like this, but it's exactly the same thing that you're used to doing in other classes like in high school algebra and all that kind of stuff. So this notation here on the top, this is the summation of all the scores in the data set. So again, this is going to indicate that you're going to be adding up every single one of those scores that you have in your observation. And then this end right here, it's a notation for sample. So typically, again, this is what we use for us to indicate how many people were part of our sample. So how many humans we interview, survey, or observe. But basically, we have an observation from them. So again, the sample is going to be our total number of observations, but again, in scientific research, psychological research, we refer to it as a sample. So here again, this is just like a summation, whereas at the bottom is the total number of observations we have. The other thing that I want to emphasize here that might be a little bit different to what you're used to is this notation right here. And this specifically is the notation for the mean of a sample. This is the mean of a sample. And we're going to see that that's going to change slightly when we talk about the population mean. But again, the mean is the average of all the scores in the distribution. And what you have to do to calculate the mean is first make that summation of all of those scores. So you're adding up every single observation you have in your data set, and you're going to be dividing that over the total number of observations, in other words, our sample. Now, in some cases, we're going to be looking at the population mean. Now, this is not super common because, again, it's very rare that we have access to the entire population, which is why we end up um, recruiting samples to make inferences about a population. But there will be some instances where we will be able to have access to every single individual that meets the criteria of the population of interest, and we can make observations from them. So for instance, SAT or ACT scores, everyone who takes that test on any given year becomes the population, and we have their scores for every single person who took it. So in those cases, we can actually get population parameters or again statistics that are relevant to the actual population. Now, to calculate the mean for the population is exactly the same process that we discussed as calculating the mean for a sample. The only thing that I want to emphasize is a little bit of a difference in the mathematical formula that we have here. So again, here, this top part, it's still referring to that summation. So again, we are going to add up every single observation that we have on the data set. Now here in the bottom, we still have what we call the notation for the sample. The only thing that is different from the one that we were working before is that this is a capital N. And this is indicating that this is truly involving everyone that would be part of this population. Whereas, as we saw earlier for the sample mean, this is a lowercase n indicating the total number of people in the sample. So actually, this would be again, the population. Technically, it's not a sample, but it's referring to the number of people that we have observations. So again, we're still working with the number of observations that we have in total, which again, in this particular case, that would mean everyone that belongs to the population, and you will have that information. And then this other notation that we see here, that is going to be the symbol that represents the mean for the population. So if you see this, that is the mean for a sample. If you see this, that is the mean for the population. But the calculation itself is going to be very similar. You're going to add up all the observations you have. You're going to divide by the total number of observations that you have. Now, the median is a score in the middle of the distribution. So whatever the median is, because this is going to change again depending on your distribution and the range of scores that you're working with, it doesn't matter, but whatever that value is, it's going to represent 50% of the scores. So wherever your mean or your median, excuse me, falls into is going to indicate that 50% of the scores are going to be higher than that one score, and then 50% of the scores are going to be lower than that one score. And again, we're going to see this in a more visual kind of way later on. Now, the median is an important measure for skew distributions. And this is going to be very important because, as we saw last time, there will be some human behaviors that naturally occur in a skew distribution, or they have a skew pattern. And as we also saw, but we're going to see a little bit more closely today, the mean is heavily influenced by those extreme scores. So those scores that are not typical in comparison to everyone else in the data set. Now, another thing to remember about the median is that they need to be ordered from low to high. So don't remember that they have to be organized. It doesn't matter if you go from high to low or low to high, since it's going to hit the midpoint, you're still going to get the answer. Now, the other thing to know about the median is, again, this 50% indication allows us to do something. It allows us to compare the performance of people within the distribution itself. And lastly, we have the mode. The mode is simply the most common score in the distribution. So whatever observation is showing up the most, that is going to be the mode of the distribution. Again, the mode and the median are going to be particularly helpful for very specific types of distributions, and we're going to discuss that later on. Okay, so here we have this practice problem. Please pause here for a couple of minutes and go ahead and do this particular task. You have a data set here that has students A to L, and it's indicating how many hours they study for, I don't know, an exam or something like that. Your task is to calculate the mean, the median, and the mode for this specific data set. Again, we just talked about very quickly about what the mean, median, and mode stand for and how to calculate them. Again, the mean, you're going to average all of these observations. So you're going to add them up and then divide them by the total number of observations you have. The median, you're going to organize them low to high and then locate that midpoint. And the mode is simply the observation that repeats the most. So go ahead and do that using these observations that you see here, and then go ahead and repeat the same task, but then go ahead and add up one more observation, which is going to be a student who says they study 60 hours. So again, make sure you pause here a little bit and then calculate the mean, median, and mode with this original data set, and then again with adding this additional observation. Hopefully your answers are looking something like this. So here I have already organized our data into low to high, just so that we can more easily see how we're going to calculate the median. But it's the same data that was presented in the previous slide. It might look differently, again, just because I organized it, but it's the same data. So again, whenever we want to calculate the mean, all we have to do is add up every single one of those observations that we have in our data set. And again, this right here is our data set, all of these numbers right here. So that's what we do here on the first step. We're simply adding those and we're going to get 84. This is the summation that we had seen earlier when we had this right here. And then we have to divide by the total number of observations. So again, how many observations do we have in this particular sample or population? So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total observations. And again, this is equivalent to how many in the sample or how many in the population. We have 12. So now we're going to divide 84 by 12 and we get 7. So the mean for this data set is going to be 7. Now for the median, we're going to, again, organize them low to high. And then we're going to start looking for that midpoint. And typically, what we're going to be doing is that we're going to be crossing out those observations until we get to the middle. So we're going to cross one by one, again, until we approach the middle. Now here we can see that because we have an even number of observations, we actually are going to end up with 2 observations in the middle. When you have something happening like this, you have to add them and divide them by 2 so that you can get the median. In this case, because both of them are 7, 7 plus 7 is going to be 14. 14 divided by 2 is going to be 7. So the median is going to be 7. And then the mode is, again, simply the observation that is repeating the most in our data set. And here we can see we have 3 5s and 3 A's. So 5 or 8 would be our modes. So those were the answers for the first task of calculating the mean, median, and mode using that data set. But then the second thing that I asked you to do was to add one additional observation, and that was an observation of 60 hours. So again, we have an overachiever of a student who decided to study 60 hours for, I don't know, this upcoming exam and so on. So we're going to do the same calculations with one more additional measure or observation, excuse me, and then we're going to see how this has impacted, if it has impacted the mean, median, and mode. So again, the processes are all exactly the same as we discussed before. For the mean, the only difference is that, again, we're making one more addition because we have one more observation. And then again, we are now dividing by 13 because we have one more observation. So for our summation, we're going to have 144, and then we're going to be dividing this by 13. So we're going to see now that our mean is 11.08, whereas previously it was 7. Excuse me. It was 7. So that is a change. Then we're going to calculate the median. And here I already have everything crossed out, so I don't have to do it again. But we can see is that at the end of the day, we end up with 7 again. So before, because we had an even number of observations, we had ended up with 2 in the middle. But now because we have an even number of observations, because we added this additional one, we are at 7. So the median is still 7. And then the mode, again, it's simply the score that is showing up the most. Here, the mode is still exactly the same. So what is this showing us? This is showing us why when we have skew distributions, the mean is not going to be the best measure of a typical score. Again, typically, if we have a normal or symmetrical distribution, which has a shape like this, remember, this is when we can draw a line in the middle and then have mirror images of the sides. This is a normal distribution. In a normal distribution, again, the mean, which is going to be at the peak of this little mountain, is going to be the best measure or the most accurate measure of a typical score. But as soon as we have a skew distribution that looks like this or like this, that is no longer going to be the case. Because the thing is, the mean is going to be very, very, very susceptible to extreme observations like this 60 right here. So again, the mean is going to follow that extreme score. Why? Because the mean is a calculation that requires you to use every single observation in the data set. So if you have something that is very extreme, like this observation, that is going to heavily impact the mean, as we could see right here. And the thing is, if you were to look at this 7 right here, and then this 11 right here, and the actual data set that you're working with, again, the 7 or the mean should be a measure of the typical score. So that means that you should be seeing numbers here in your data set that are exactly at 7 or really close to 7. So if that were to be the case and you look at this ones, it's like, okay, yeah, actually I can see there's multiple 7s, there are some 6s, there's some 8s that are really close to 7. So it seems like the mean, it really is doing a good job here of describing the typical score. But when you look here, and the mean is 11, and then you look at these observations, first of all, we don't have any observations that are at 11. And then we don't really have any observations that are close to 11. 10 would be the closest to 11, and then 60 is completely the other side. So when it comes to using the mean, when we have an extreme score like 60 here, we are no longer having a mean that is descriptive of a typical score. This mean is no longer as accurate as it could have been if we had not the presence of an extreme score. So again, when we have skew distributions like this ones right here, the median and the mode are going to be best measures of the typical score. Why? Because as we can see, these two are still the same as in this data set. They're not as affected by the presence of extreme scores, which was the case with this 60. So at this point, it is worth reminding ourselves the different shapes of distributions that we can have. And again, see how these measures of central tendency work with the various distributions. So again, in general, um, the mean is going to be the most common reported measure of central tendency because it tends to be a good representation of all the scores of the distribution because all the scores of the distribution or in the data set are used when we're calculating the mean. But again, because we're using all the scores in the data set, this means that those extreme scores are also going to be part of the calculation. And as we just saw, this is going to be very problematic because it could drastically change our mean in a way that is no longer representative of the data set itself. So the mean is going to be the best measure of central tendency or of the typical performance, the typical behavior when the shape of the distribution is normal. So again, we want to see this kind of shape where both of the tails seem to be balanced and that if I were to want to draw a line right at the middle, again, these images are going to be mirror images of each other. So again, when the distribution is normal, then the mean is going to be the best measure of the typical behavior of whatever is our study at that point. But as soon as we have skewed distributions, the mean is not going to be a good measure of the typical score. Why? Because skewed distributions means that we have extreme scores in our data set. That's why we have either this tail or this tail happening, because we're going to have very few observations that are gonna fall on these areas. And remember that we typically draw the distributions with like these lines, as you can see, the bluish lines, but they are representing bar graphs underneath that area. And again, that line is following the height of the bars. So don't forget that when you're seeing distributions, because that is very telling. Again, this means that in this positively skewed distribution, most of the scores are located on this side, but we have one extreme score right here that is making this tail not be balanced. It's going to be all the way here rather than ending somewhere here, which would create asymmetrical distribution like the one we see in the middle. On the other side, again, when we have a negatively skewed distribution, we have something very similar happening where we have a very extreme score, but it's on the opposite tail than in a positively skewed distribution. But the main idea is the same. We have a bulk of the scores happening in one section of the distribution, which we can tell by the height of this distribution line right here. Because again, remember that it's going to be showing, or it's representing the height of the bars, which is the height of the bar, the height of the frequency, right? So most observations are going to be located here at the peak with very few on the sides. And again, it's making this tail go this way. Whereas this other extreme score is making the tail go this way. So again, skewed distributions by definition are skewed because they have extreme scores. And we already saw that the mean is very susceptible to extreme scores. So as soon as we have skewed distributions, the mean is out the window, and instead we're going to use the median as the gold standard for describing typical behavior. And in these distributions that you see here, I love this image because it really shows you how the mean, median, and mode are related to each other when we have either a symmetrical distribution or skewed distributions. So let me go ahead and clean this up so that we can more clearly see this. Okay. So here, when we're looking at the symmetrical distribution, Again, this is a distribution where if I draw a line in the middle, both sides are mirror images. Now, in this type of distribution, and actually in, well, and let's get started with this one. In this type of distribution, the peak of this little mountain represents the mean. So the peak, because again, think about how it's representing a bar. That is the highest point that a bar is going to reach in a distribution. In this case, again, the mean is going to be represented by that, which is the highest point. So this is the most typical behavior that there is in the data set. In a symmetrical distribution, the mean is going to equal the median, and the median is going to equal the mode. So all of those three variables in or statistics, excuse me, in a symmetrical distribution are going to be exactly the same. So if you have a mean that is 6, the median is going to be 6, the mode is going to be 6. If you have a mode that is 12, the median is going to be 12, the mean is going to be 12. Now, again, this is going to change when you have skewed distributions. And you can see it again represented by these diagrams. Now, whereas in a symmetrical distribution, they're all towards the middle, they're going to change when they are skewed. And specifically what we see is that drastically what will change is going to be the mean. The mean is going to follow the direction of those tails. So in the case of a positively skewed distribution, remember that this means that is going towards the higher values. So if this goes from 0 to 7, the mean is going to become larger than the median. The median is saying that it's right here, whereas the mean is now right here. If we have to label this ones, this is probably around, I don't know, maybe like a 4 or something like that. This is going to be more like a 5 or, you know, something like that, right? So the mean is going to be greater than the median. This is going to be very important for you to remember. So again, the mean is going to be greater than the median. And then on a negatively skewed distribution, we see the mean is going to follow the tail, or where the extreme score is. Again, remember, there's like one observation that is being represented here. And in this case, again, negatively skewed distribution is that it's following the lower range of scores in whatever the distribution is. Again, it's moving towards this direction. So in this case, the mean is going to be less than the median, because we have the mean being here and we have the median being here. And again, this is going to score lower than the median. So make sure again that you understand how they relate like this when it comes to a positively skewed distribution and a negatively skewed distribution. Now I'm going to clean this up again. And there is one last thing that I want to emphasize on this. See? And that is that I mentioned that the peak of the distribution is typically going to be the frequency with the, or the outcome with the highest frequency. Why? Because this is going to be representing the tallest bar graph in the distribution, in the frequency distribution. And we can see that in this point, and I'm so sorry, let me clean this up again just so it can very clearly be seen. Usually where you see the little hump is where you're going to have the highest bar, which means, again, it's the outcome with the highest frequency. There we go. And you're going to see that in a symmetrical distribution, again, this is going to be fine. The mean, the median, and the mode are located exactly here. So all of those are good measures of central tendency. The mean will be the best one because it's using all the scores. But in the skew distributions, as we mentioned, the median is going to be the best measure for us to use of typical behavior, because we can see that the mean, again, gets moved in the direction of the tail. And actually, let me change the color of this very quickly, just so I can show you something. So the mean is going to be in green now, right here, and then I'm going to put the median in purple. So we'll see that the median is slightly affected also by the presence of that extreme score, because we do add one more observation that we have to keep in mind when we are finding the midpoint. But because it's not based on, for instance, like the mean, adding all of them, it's not as influenced by it. So if I were to ask you between the median and the mean, which is closer to the hump that is represented by those red dots, which again is representing a bar graph, the bar that with the highest level, which is representing the more frequent observation, which is representing the typical observation in the sample, you will see that the median is closer to that rather than the mean. Why? Because again, the mean is extremely susceptible to extreme scores and is going to follow the path of those extreme scores. Now, here we have another visual example of this. Again, if I were to draw a line on this, we will have something like this. So we have a negatively skewed distribution, right? Hopefully, I know, again, I'm not able to draw as well because I'm working with a mouse. But again, if we follow those bars, it's going to create something similar to this negatively skewed distribution here. So we have a negatively skewed distribution here. And again, we can see that the mean is going to follow this tail because we have some extreme observations here. And again, the mean is going to be less than the median. So don't forget this type of associations because they're going to be important. Again, the little hump is somewhere here. So this is actually the outcome with the most frequency, or the most common, the most typical. And we see that the median, which is here, and then the mean here, the median again is going to be closer to this. But now here we get to see this with real numbers. So we see that the mean says that is 78.67. So the mean is falling somewhere here, which is represented by this bar right here. Again, by the height of the bar, we can tell that's not actually the case. Most people are performing right here. And if we look at the median is 80. The median is going to be here, which is now represented by this bar. So the median is a better measurement of typical behavior when we have a skewed distribution. Earlier, I had mentioned that there are some variables of interest that exist naturally as a normal distribution, whereas others exist more naturally as a skewed distribution. Also, when I introduced myself for this course, I mentioned that some of my research has to do with intimate partner violence. So I do a lot of work where I have to ask participants, their perpetration of abuse towards their romantic partners. So I want you to think about the frequency of intimate partner violence perpetration. So again, if I were to ask participants, how many times have you abused your partner, and I give them this answer choices right here, then how do you think this is going to be distributed? So here we have, again, kind of like a clean canvas for us to work with. Again, we have the y-axis here, which is always going to be our frequency when we're doing frequency distributions. And then here we have our x-axis, which is going to represent our scores, our values, all that kind of stuff. In this case, this is going to be perpetration of IPV. And I'm going to do my best to write this for penetration. Now I gave participants the option to go from 1 to 7. So we're going to have 1, 2, 3, 4, 5, and then 6. And based on my experience and social desirability bias and all that kind of stuff, most people are going to respond that they've never done this. So remember the frequency values go from 0 to something, right? So the height of the bar is the frequency. It's represent the frequency because it's going to tell us where in the y-axis is going to hit. So again, most people will say that they've never hit their partner or they've never abused their partner. Some people might say like, it happened once, I'm sorry. Other people might say like, okay, it has happened more than once. But most people are going to say, again, never, right? And very few people are going to say, yeah, I've hit them all the time, kind of thing. So it's going to create, again, not a normal distribution. Remember, this is, actually, that it's so poorly drawn that doesn't look normal at all. So again, it's not going to create a normal distribution. It's going to create something like this because the extreme score is going to be located on this tilt. We're expecting most people to say, I've never hit my partner. And very few people to say like, I do this like all the time. So if that is the case, again, we're going to have a skew distribution. And because this is a variable that I work with a lot, I need to know that. Because if I were to get the mean of this distribution, I'm going to get inaccurate information about what is the typical type of behavior in a relationship, right? It's going to make it look like more people are abusive to their partners than they actually are. So in this case, it will be very important for me to know that it's not normally distributed, that it actually is positively distributed so that I can properly analyze the data. So again, in this case, the frequency of intimate partner violence perpetration is going to be positively skewed because most people are going to say that they haven't had any incidents of IPV perpetration, whereas only a small group of people would say that they have had a higher number of incidents, creating a long tail on the right. So again, we've already talked about the mean is the best measure of central tendency when we have a normal distribution. The median is the best measure when we have a skewed distribution, but also the median is going to be very good for ordinal data or open-ended categories, like when you're asking students again, how many hours have you studied? The mode is going to be better when we have categories like dog, cat, fish, bird, or when we have bimodal distributions, because we're only going to have two possible outcomes that, again, we can very easily look at by seeing which is the most common one. Well, this is the most common one. And here is a flow chart that can help you decide which measure of central tendency is the best to use, depending on the type of scale that your measure actually has. Okay, so we've discussed central tendency already. Again, central tendency is the mean, the median, and the mode. We talked about how to calculate each one of those, and then we've talked about when it's best to use each one of those. Now we're going to move on to another thing that is very important that we can see based on how our distribution looks like. And this is going to be variability, which is simply a description of how different the scores are from one another in the distribution. So how much they vary in comparison to each other. We're going to have high variability or low variability. High variability is going to be indicated by a spread out scores. So again, we're looking for something that, a distribution that is going to be very wide. And then low variability is going to be represented by scores that are similar to each other and clustered to each other. So here we have a visual for this. Again, we have the blue distribution or the blue line distribution that is representing low variability. And we can see that this distribution is very narrow. So visually, again, it looks very narrow. If I were to measure the width of this distribution, is going to be smaller than the one for high variability. For high variability, you see that it's a very wide distribution. And what that is implying is that, again, the scores are more spread out. So when we have high variability, again, we're going to have scores that are going to be spread out. When we have low variability, we're going to have scores that are very similar and clustered. So again, visually, make sure you understand how the shape of the distribution, what the shape of the distribution implies in concerns to variability. Now here on the other side, we have a different example. This is more by using bars rather than just the lines of those distributions. But remember that the bars are showing you how the distribution looks. So if I were to draw those lines here, it's going to look something like this. Whereas if I draw the lines here, it's going to look a little bit more like this. So again, you can see that in comparison to each other, this one is going to be wider, which means that it has higher variability. Whereas this one right here is going to be narrower in comparison to the other one. So that means that a lot of the scores are clustered together. So this one has low variability. So again, make sure you understand that. And then the other thing we see is here with the actual scores, these scores go from 5 to 9, whereas these scores go from 4 to 10. So we have more variability again. The scores are represented by different outcomes than this one. This is why this distribution is wider in scope. It also has a higher range of possible scores than this one, which means that again, for this type of distribution, we have similar scores, that meaning that in comparison to each other, they're kind of staying close to the same kind of value, and they're more clustered together than the ones that are represented here. Now, before we move on to the next page, I want to talk about why this is important. So again, variability in general is just going to speak about the spread of the scores. And this is going to be very important because of the central tendency. When we have, again, because both of these ones, by the way, are going to be kind of normal distributions. Now, the widths are different, but I could still try to split this in halves, and they will be kind of similar to each other, right? Now, again, we've talked in the past that the peak of the distribution is going to be the mean. So the mean is going to represent the most typical score in the distribution. And if you have a lot of scores, like this one, in this distribution that are close to the mean, then that means that these scores are better represented by the mean. But then in the orangey distribution, we have all these scores right here and all these scores right here that are farther away from the mean, which again, the mean is right here. So if we go all the way down, this is the mean for this distribution. So these scores right here are less represented by the mean. So ideally, when we're looking at distributions, we want to have distributions that have low variability because that's going to make our measurements more accurate and better representative of the behavior of interest that we have. So now we're moving on to a different concept, but very closely related, which is standard deviation. And standard deviation is a measure of variability that specifically is going to represent the average difference between the scores and the mean. So again, when we talked right now about the distributions, I said that the closer the scores are to the mean, the more representative the mean is to those scores. The farther away those scores are from the mean, the less representative is going to be of those scores. So again, ideally we want to see that there is low variability in our distributions because we have more trust in our findings that they are truly being represented by the statistics that we're working with. The standard deviation, again, is going to be a measure that is going to give us an indication of how far away the scores are from the mean specifically. Again, why? Because the mean is what we're using to describe the typical behavior of the sample or the population that we're working with. And again, the standard deviation will give us an indication of how, in other words, how much we can trust that the mean is actually representing all of the distribution. A large standard deviation will mean that the scores are going to be spread out, and a small standard deviation is going to indicate that the distributions are packed close together or closer to the mean. So what this means is that, again, in terms of variability, high standard deviation is going to equal high variability. Again, because there is, we're going to be working with something, actually, let me do that again. We're going to be working with something that is like this. It's wider. So again, we have more scores or a larger range of scores that we're working with. Now, in terms of low standard deviation, so again, low standard deviation is going to equal to lower variability. Because again, we're working with distributions that look more like this. So we're going to have scores that are packed close to each other. So again, make sure you also understand what is the association between standard deviation and variability. So for the rest of today's class, we're actually going to learn how to calculate the standard deviation. And through words, it might seem way more complicated than it actually is, but I'm going to walk you step by step. And always remind yourself that you're not doing anything complicated. The most complicated thing you're doing here is probably getting the square root of a number. All of you know how to do this. So again, don't let your mind trick you into thinking that you're not going to be able to do this. Again, these are easy calculations. I'm going to walk you step by step on how to do these things. And again, I can guarantee every single one of you can do this. So here's typically how you're going to see this in your homework assignments or in your exams. So let's first get familiarized with how the table that we're going to be working with is structured. We have three main columns, which again, we have the raw score right here, we have deviation right here, and then we have square deviation right here. So we have three main columns. Typically, for the raw scores, I will be giving you this information, including the mean. So I'm going to give you all the individual observations that exist in the particular data set and what is the mean for that data set right there. So we read the columns going down, but then per row, all that information is relevant to that raw score right here. So again, all of this is relevant to this score right here. So per row, we're looking at individual observations. Per column, we're looking at all of them. Now the mean, again, this is the mean for this set of numbers right here. Oh, the other thing that I wanted to emphasize, because sometimes students get confused with this row right here, since it's labeled mean, that indicates that this is the mean of this column. This, whatever we calculate here, is going to be the mean for this column. And then here, that's going to be the mean of this column. And then this right here is labeled standard deviation. So this score right here is going to be our standard deviation. Now let me clean this up. The other thing I want to emphasize are the formulas that I've left here for you so that you can have them handy. And these are going to be the formulas we're going to be using, or the equations that we're going to be using, so that we can calculate the information that is going to go in these rows right here. Now, the deviation is going to be the distance between one score from the mean. And so what we're going to be seeing is that we're going to get the raw score, which is already provided to you in this column, and we're going to subtract the mean, which is already provided to you right here. So you have all the information you need. All you really need to do is to substitute that number, or actually there's two numbers, where they belong to. The raw score, that will mean 55. So to do the first one, will be 55 minus 75 equals negative, 20. And make sure that you carry the negative correctly. And then for square deviations, let me clean this up. Once you calculate your deviation, you're going to have the information that you need, because square deviation, all it is deviation times deviation. So you're multiplying the number by itself. You can also see this noted as deviation squared, which is exactly the same thing. So these two things mean the same thing. They're just different ways of writing the equation. So if here we had negative 20, then here this is going to be negative 20 times negative 20, which should be, I'm sorry, 400. And again, because we have two negative numbers, this is going to turn into a positive number. So make sure you remember all of those things as well. So for now, go ahead and again, pause the video here and take a couple of minutes to fill up this table. So up until now, go ahead and do right here. Oh, sorry, I don't have to click certain. So do up to the point of the mean for both the deviation and the square deviation. So go ahead and find the deviations here, and then find the mean of those deviations. How do you find the mean? You're going to add up all of these scores and divide them by the total number of observations. The mean, in this case, does not count as an observation, okay? Your observations are simply these ones right here. And then you're gonna, once you find the deviations, you're going to find the square deviations. You're gonna fill this up to here. And then you're going to get the mean right here. And then this that you see here, this SS, it just says summation. It's sums of squares. So this row right here is going to be the addition of all the scores you have right here. So this is the sum. And then here you'll have the mean. And then once you have the mean, I'll walk you through what you need to do for the standard deviation. Okay, so here we have our first column completed, which are the deviations. And again, for the deviations, the equation we're using is the raw score minus the mean. I gave you information for all of the raw scores in the data set, and I give you the mean of those observations. So all you have to do is work with this equation and then place those numbers where they belong to. The raw score goes first, and then we're subtracting the mean, which is 75. In this case, we have negative 20, and again, be careful with the negative. Then we have a raw score of 60, so that number goes first, minus 75, which is the mean, again. and that's going to give you negative 15. Then you have a raw score of 65, so we put 65 first, minus the mean, which we already know is 75, so you're going to get negative 10. Then you're going to go to 70, you have 70, which is a raw score, minus the mean, which we already know is 75, so you're going to get negative 5. And you're going to continue. Just going to do one where we have a positive number. So here you have a raw score of 85, which again is the raw score that's provided here. You're subtracting the mean, which we already know is 75, and you're going to get 10. So again, you're going to be able to possibly get negative numbers or positive numbers, and it's very important that you're doing those calculations correctly. So if it's a negative number, you got to carry that negative number. Now, sums of squares, like I said, it's just simply, well, right now it's represented by this row right here. Let me clean that off though. And that all it means is that you're adding up all of these values right here, or all of these values right here. And then this column right here, or excuse me, this row, so everything here is the mean of the respective columns. You already have the mean of the raw scores, and you can also get the mean of the deviations. Now, here is something that I want to point out. The mean for the deviations will always be equal to 0. So this is a good way to check that you're doing your work correctly, because if after you add up and then divide all of these observations, so you add all the observations and then divide them by the total number of observations, aka you're getting the mean should equal to 0. If it's not equal to 0, it probably means that you've done something wrong in this calculations, and it's best to check your work at this point before you move on, because if you make a mistake here, that mistake is going to carry on to the next part. Okay, and then after you have those deviations, which again, hopefully all of you were able to calculate correctly, we would move on to the squared deviations. Again, I gave you that formula in the past slide, and then we're going to see that in the next one. Okay, so now that we have our deviations, we have the information that we need to calculate this third column, which is squared deviations. And again, all we're doing here is taking, we're squaring the deviation, which is the same thing as saying deviation times deviation. So we're multiplying this number by itself. Now here again, I have it as it's a number squared. But you can also do deviation times deviation. So this is the same as negative 20 times negative 20. And again, the main thing that I want to emphasize here is that you are familiar with what are the rules for negative signs. If you multiply a negative number times a negative number, you're going to get a positive number. If you multiply a positive number times a positive number, you're going to get a positive number. But if you multiply a negative number times a positive number, you're going to get a negative number. Those are going to be very important, because if you're not familiar with those rules and you end up writing this as negative 400, your answer is going to be wrong. But okay, so you're going to individually do that for each one of those, which is already filled up in here. And then we have again this column right here, which is the sums of squares. And again, all that is saying is that you're going to grab all the different observations right here, and you're going to add them up. So that's all that it has happened right here. This is the total of all these individual scores being added up. So now that we have that information, we're going to be able to take the variance, which is going to be the mean of squared deviations. And again, don't let this terminology scare you. It literally is you taking the mean. You know how to do this. So again, the only difference here is that it has been broken down into different steps. But again, all you did is add up all of these observations, which is this value right here. And then you're going to divide by the total number of observations we have, which we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, this is not an observation, that is the mean of that column. So we have 12 observations, and we get the mean of 129.17. This is, again, the variance or the mean of squared deviations. So that is the third step in calculating the standard deviation. And then now we are on our last step. And here we have again how we calculate the standard deviation. Like I mentioned earlier, the hardest thing you're going to do is taking the square root of a number. So you're absolutely able to do all of these things. You just have to remember what you're supposed to do per each one of the steps, and then make sure that you take notes of the formulas that we've been using for steps. But again, all you're doing is subtracting, squaring numbers, and taking the square root of numbers and getting the mean of some numbers. These are all simple calculations that all of you should know how to do right now. So again, with the standard deviation, now we have this number right here, which is the mean of square deviations, and also called the variance. So this is also, again, known as variance. And now that we have the number, again, we're going to get the square root of the number, which in this case is 11.37. So this data set has a standard deviation that is equal to 11.37. Now, make sure that, again, you're familiar with how to do all of these calculations, the mean, median, and mode, and as well as the standard deviation, because you will be asked to do this in homework assignments or in your exams.